Good afternoon, everyone, mga Batang MANDunong. Welcome to our 7th week, to our review lesson in our Project SOAR, the series of online academic reviews in mathematics. I hope nag-enjoy tayo in the previous review lessons sa mga previous weeks na ibinigay sa atin ng mga mathematics teachers natin. Now, for our week 7, before we proceed, and I would be able to introduce to you our review teachers, let me acknowledge, of course, our educational leaders, Dr. Romela M. Cruz Zese, our OIC, Schools Division Office Superintendent, Dr. Aurelio G. Alfonso, Doc Aga, our OIC Assistant Superintendent, Schools Division Office, our Dr. Aline G. Mendoza, the Chief Education Supervisor for Curriculum Implementation Division, our Mrs. Emma G. Arubio, the Chief Education Supervisor for Schools Operations Governance Division, and of course, aming matsugat ditong Education Program Supervisor in Mathematics, Mr. Mathtuto Rodelas. Okay, so I hope this afternoon, mga grade 7 Mandunong, you will be able to enjoy and sit back, relax as you listen and then go beyond the review lessons ng ating magiging teacher sa hapon na ito. To introduce to you our review teacher, okay? He graduated Bachelor of Science in Education, major in Mathematics at University of Makati in 1995. High school pa po ako nito. He earned these 39 units of Master of Arts in Teaching Mathematics at Philippine Normal University, a former high school teacher at Sacred Heart Institute in Muntinlupa in 1995 to 1997, a high school teacher and coordinator of student affairs at Nami Polytechnic Institute from 1997 to 2015, and a former part-time instructor in the College Department of NAMI and STI Santa Mesa from 2009 and 2015. Mga bata, ladies and gentlemen, our review teacher for Project SOAR for grade 7 to week 7 from Ilaya Barangka Integrated School, Mr. Jomy B. Yocampo. Hi, sir. It's your turn po.
Thank you very much, Mr. MC, for that generous introduction. Hello, everyone. I am Mr. Jomy de Los Santos Yocampo, a grade 7 mathematics teacher of Ilaya Barangka Integrated School. A warmest greetings to my mathematics coordinator of Ilaya Barangka Integrated School, Mrs. Erlina C. Lapada, together with our school head, Mr. Joseph V. Alegre. For today, I'll be discussing with you Module 7A, estimating the square root of a whole number to the nearest hundredths by using square root algorithm. Let me present to you the objective of this module. To estimate the square root of a whole numbers to the nearest hundredths by using square root algorithm. Allow me to present to you the key concepts of the lesson. When you take the square root of a number, you may get a decimal number. If you're able to get the whole number as an answer, then the original number you're finding the square root of is a perfect square number. Example of the list of perfect squares include the numbers 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, 225. When a radical is not a perfect square, estimating square roots is a valuable tool. When asked to estimate the value of a radical between two consecutive integers, find the two perfect squares that are slightly less and slightly more than the radicand. Example, estimate the square root of 645 to the nearest hundredths. First, group the numbers under the root in pairs from right to left, leaving either one of the two digits on the left, 6 in this case. For each pair of numbers, you will get one digit in the square root. To start, find a number whose square is less than or equal to the first pair or first number and write it above the square root line. So we have the square root of 625. Our first digit is 6. The nearest square root of 6 is 2. Square the 2, giving 4. Write it underneath the 6 and subtract, then bring down the next pair of digits. Then double the number above the square root symbol line and write it down in parentheses with an empty line next to it as shown above. Next, think of a single digit that something could go on the empty line so that 40-something times something would be less than or equal to 245. 45 times 5, that is equal to 225. If it is 46 times 6, that is equal to 276. So in this case, 5 works. Write 5 on top of a line. Calculate 5 times 45. Write that below 245. Subtract. Bring down the next pair of digits. In this case, the decimal digits 0, 0. Again, write 5 on top of a line. Calculate 5 times 45. Write that below 245 and subtract. Bring down the next pair of digits. In this case, decimal digits 0, 0. Then double the number above the line 25 and write the doubled number, that's 50, in parentheses with an empty line next to it as indicated. Then again, double the number above the line 25 and write the doubled number 50 in parentheses with an empty line next to it as indicated. Think what single-digit number something could go on the empty line so that 500-something times something would be less than or equal to 2,000. Let's say 503 times 3, that is equals to 1,509. If it is 504 times 4, that is equals to 2,016. So in this case, 3 works. Think what single-digit number something could go on the empty line so that 500-something times a particular number would be less than or equal to 2,000. Let's say 503 times 3, that is equal to 1,509. If it is 504 times 4, that is equals to 2,016. So in this case, 3 works. Calculate 3 times 503, write that below 2,000, subtract, then bring down the next digits. Once again, you calculate 3 times 503, write that below 2,000, then subtract, bring down the next digits. Then double the number 253, which is above the line, ignoring the decimal point, and write the doubled number 506 in parentheses with an empty line next to it as indicated. Again, you double the number 253, which is above the line, ignoring the decimal point, and write the double number 506 in parentheses with an empty line next to it as indicated. So you have 5,068 times 8, that's 40,544. If it is 5,069 times 9, that is equals to 45,621. In this case, 49,100 is less. So 9 works. Again, 506 times 8, that is equal to 40,544. 5,069 times 9, that is 45,621, which is less than 49,100. So in this case, 9 works. Now let's proceed to Module 7B. Estimating the square root of a whole number to the nearest hundredths by using the divide average method. Allow me to present the objective of this module: to estimate the square root of a whole number to the nearest hundredths by using the average method. Remember that there are a number of ways to calculate square roots without a calculator. Here is divide and average method. Step number 1, you estimate or find the perfect square root as close as possible in your number. Step number 2, divide your number by the square root. Step number 3, calculate the average of the result in step 2 and the root. And lastly, step number 4, use the result of step number 3 to repeat step number 2 and 3 until you have the number that is accurate enough for you. Let's take this first example. Let's estimate the square root of 695. Let us guess for the root as 25. So 695 divided by 25 is equals to 27 and 8 tenths. Next step, so you have 25 plus 27 and 8 tenths divided by 2. Our answer is 26 and 4 tenths. So 695 divided by 26 and 4 tenths is equals to 26 and 3,257 ten-thousandths. And then round off, our final answer is 26 and 33 hundredths. Second example, let's approximate the square root of 128. Note that using a calculator, the square root of 128 is equal to 11 and 31 hundredths. Here is the solution. We know that the square root of 128 is between 11 squared and 12 squared. Between the two, it is nearer to 11 squared. So the first estimate is 11. Next, we divide 128 by the first estimated perfect square and average. It would be the quotient. Second estimate, let's divide. 128 divided by 11 is equals to 11 and 6 tenths. If it is average, 11 and 6 tenths plus 11 divided by 2, our answer is 11 and 3 tenths. Our second estimate is 11 and 3 tenths. Our third estimate, divide. So we have 128 divided by 11 and 3 tenths is equal to 11 and 327 thousandths. In finding the average, we have 11 and 3 tenths plus 11 and 327 thousandths divided by 2 is equals to 11 and 3,135 ten-thousandths, and round off to the nearest hundredths, our final answer is 11 and 31 hundredths. Let's have our third example. Let's approximate the square root of 325. Using the calculator, the square root of 325 is equals to 18 and 300ths. Here is the solution. We know that the square root of 325 is between 18 squared and 19 squared. Between the two, it is nearer to 18 squared. So the first estimate is 18. Next, we divide 325 by the first estimated perfect square and average. It would be the quotient. Second estimate. Let's divide 325 divided by 18 is equal to 18 and 500ths. For the average, we have 18 and 500ths plus 18 divided by 2 is equals to 18 and 300ths. Second estimate, 18 and 300ths. So our third estimate, let's divide 325 divided by 18 and 300ths. That is equal to 18 and 25 thousandths. For the average, so we have 18 and 3/10 plus our average, which is 18 and 25 thousandths divided by 2, that is equals to 18 and 275 10,000ths. Then round off to the nearest hundreds. Our final answer is 18 and 300ths. Now let's proceed to Module 7C, estimating the nth root of the given whole number. Allow me to present the objective of Module 7C, to estimate the nth root of the given whole number. Here is the key concepts of the lesson. Let's define the nth root of a number. Let A and B be real numbers, and let n is greater than b a positive integer. If A is equals to b raised to n, then b is an nth root of A. If A is equals to b raised to n, means the nth root of A is equal to b. Whenever we see a radical symbol in math, you know you are dealing with roots. Radical symbols look like check marks with a horizontal line attached. The small number above the check mark portion, if there one, called an index or degrees, tells you what root to find. The big number under the radical symbol is called a radicand and tells you what to take the root of. So in this case, we have the cube root of a plus b. So a plus b is the radicand. The root is cube or 3. When we say radicand, it is the thing you are finding. So in here, you have the radical sign, the symbol that means the root of. In the cube root a plus b, the small 3 here is called the degrees or index. When we say degrees or index, it is the number of times the radicand is multiplied by itself. If it is 2, means square root. If it is 3, means cube root. After that, they are called the fourth root, the fifth root, and so on. If this is missing, it is assumed to be 2 or the square root. Roots are the inverse of exponents, such like multiplication is the inverse of division. Roots or radicals, the opposite operation of applying exponents. We can undo a power with a radical, and we can undo radical with a power. For instance, if we have 2 squared, we get 4. And if we take the square root of 4, we get 2. A root of degree 2 is called the square root, and the root of degree 3 is a cube root. Root of higher degree are referred by using ordinal numbers, as in the 4th root, the 5th root, the 6th root, the 20th root, and etc. The common root is the square root. First, we will define what square roots are and how you find the square root of a number. Then, we will apply similar ideas in evaluate and truth. Square root. Let's define square root. For any real numbers a and b, if a squared is equals to b, then a is a square root of b, or square root of b is equals to a. We can also write square roots using b raised to 1/2 is equals to b. To find the square root of a number, you want to find some number that when multiplied by itself will give you the original or given number. In other words, to find the square root of 25, you want to find the number that when multiplied by itself gives you 25. The square root of 25 then is 5. Cube root. The definition of cube root for any real numbers a and b, if the cube root of a cube is equals to b, then a is the cube root of b, or the cube root of b cube is equals to a. We can also write square roots using b raised to 1/3 is equals to the cube root of b. To find the cube root of a number, you want to find some number that when multiplied by itself thrice gives you the original or given number. In other words, to find the cube root of 8, you want to find the number that when multiplied by itself thrice gives you 8. The cube root of 8 then is 2, because 2 times 2 times 2 is equals to 8. Here are some examples of perfect cubes. 1 is a perfect cube, which is equals to 1 times 1 times 1. 8, which is equals to 2 times 2 times 2. 27, that is equals to 3 times 3 times 3. 64, that is equals to 4 times 4 times 4. Next, you have 125, which is equals to 5 times 5 times 5. Then you have 216, that is equals to 6 times 6 times 6. Then you have 343, that is equals to 7 times 7 times 7. Another one, you have 512, that is equals to 8 times 8 times 8. Then you have 729, which is equals to 9 times 9 times 9. And you have 1,000 is equals to 10 times 10 times 10, which is equals to 1,000. Let's have this first example. Find the cube root of 625. Finding the cube root of a number is the opposite of multiplying a number by itself 3 times. In other words, it's the opposite using an exponent of 3. Let's look at it mathematically. A certain number raised to the 3rd power is equals to 625. We're going to find the value of x. To find the cube root of 625, we need to figure out that x is in this equation. What number can we raise to the power of 3 to equal 625? So, 15 cubed is equals to 15 times 15 times 15, which is equals to 625. 15 multiplied by itself 3 times give us the number we are looking for. Thus, the cube root of 625 is equals to 15. Let's take a look with the second example. Find the 4th root of 10,000. Finding the 4th root of the number is the opposite of multiplying a number by itself 4 times. In other words, It's the opposite using an exponent of 4. Let's look at it mathematically. A certain number raised to the fourth power is equals to 10,000. So we're going to find for the value of x. To find the fourth root of 10,000, we need to figure out what x is in this equation. What number can we raise to the power of 4 to equal 10,000? So 10 to the fourth power is equals to 10 times 10 times 10 times 10, which is equals to 10,000. 10 multiplied by itself 4 times give us the number we're looking for. Thus, the fourth root of 10,000 is equal to 10. Let's proceed to Module 7D, plotting irrational numbers up to square roots on a number line. The objective of this module is to plot irrational number up to the square roots on a number line. Here is the key concepts of the lesson. The set of real numbers. It is all numbers that can be shown on a number line. This includes natural or counting numbers, whole numbers, and integers. It also includes rational numbers, which are numbers that can be written as a ratio of two integers, and irrational numbers, which cannot be written as the ratio of two integers. When comparing two numbers, the one with a greater value would appear on the number line to the right of 0, and the smaller value would appear on the left of 0. Example, if we're going to plot the square root of 12 in the number line, this number is between 3 and 4, principal roots of 9 and 16. Since the square root of 12 is closer to 9 than 16, the 12 or the square root of 12 is closer to 9, then plot the square root of 12 closer to 3. Let's take a look with example number 2, the square root of 5. We're going to plot that one in the number line. So the number is between 2 and 3. Principal root of 4 and 9. Since 5 is closer to 4 than to 9, so 5 is closer to 2 than to 3, then plot the square root of 5 closer to 2. Example number 3, the square root of 27. Let's plot this one and the number line. This number is between 5 and 6. The principal roots of 25 and 36. Since 27 is closer to 25, then 27 or the square root of 27 is closer to 5 than to 6. So, plot the square root of 27 closer to 5. Thank you for watching. This is again Mr. Jomy Yucampo. Goodbye.